When talking about physics, I like to start with a truth that many people underestimate. Nature does not operate with neatly separated drawers, the way humans usually organize everything. We tend to think that this is one phenomenon, that is another phenomenon, and the job of physics is to write more and more new laws to describe each one. But if you look deeply enough, you will see that nature does not like that kind of complexity. It prefers simplicity. It prefers to gather things that seem completely unrelated into a bolder, more unified story. And every time humanity suddenly realizes that two phenomena are actually just one, the entire field of physics steps into a new era. Let's start with Newton. Before him, people believed that the world beneath our feet, where an apple falls, and the world up in the sky, where the moon moves, obeyed two completely different sets of rules. But Newton said, no, it's just one kind of motion, governed by the same force. A simple statement powerful enough to shatter a 1,000-year-old conception. The first great unification. Then Maxwell appeared, and I always loved the way he made everything look both elegant and mind-blowing. Electricity and magnetism were once seen as two separate mysterious phenomena, each puzzling in its own way. But Maxwell gathered them together with just 4 equations. And when he solved them, he discovered something that shook the world. Those equations said there is a kind of wave that propagates at exactly the speed of light. That forced him to draw a conclusion no one dared to think. Light is an electromagnetic wave. The story became a little simpler. The world became a little less fragmented. Einstein continued that tradition by unifying space and time into a single structure. You cannot say this is 1 second without saying this is for whom. Speed changes time. Distance changes too. And then Einstein unified energy with mass through the equation that even people who hate physics remember. E equals sign msa gauge. Nature kept shrinking into an ever more unified framework, but it didn't stop there. Quantum mechanics arrived. And if you thought the previous unifications were strange enough, wait until you hear this particle and wave are not two different kinds of entities. They are two manifestations of the same thing. An electron can behave as a wave when you're not looking, then instantly become a particle the moment you decide to measure it. It switches roles so quickly, it drives every philosopher to despair. And every time we think we've understood, nature throws in another twist. What fascinates me most is this. In every major unification in physics, Newton, Maxwell, Einstein, quantum light is always at the center. It is the clue that leads us to those truths. It is the key that nature keeps offering and then pulling back, as if teasing us. Light appears at every most important turning point, yet it itself is the most elusive entity. It is always present, but it never stands still. And when you look really closely, you see the paradox. Light helps us unify everything, yet it is the very first thing that shatters all intuition. When you think it is a wave, it behaves like a particle. When you think it is a particle, it interferes like a wave. When you draw a reasonable path for it, it immediately destroys that path. It is the perfect proof that the universe does not care about how humans want things to work. It only follows its own way and forces you to accept it. All those unifications lead us to a bigger question. If light is so central, why is its nature so difficult to grasp that every attempt to assign it a path fails? What gives it the power to overturn every classical model with just a simple experiment? And more importantly, why does nature so stubbornly hide what we thought was the most obvious thing? The journey of a single photon. This is exactly the point I want you to feel. Physics is the journey of unification. But to go further, you must be willing to abandon the most familiar notions. Because light, the thing we thought we understood for thousands of years, is about to show that human intuition is not enough to describe the universe. And then comes the photon, the breaker of all intuition, the destroyer of every attempt to assign it a path. You know what's the funniest thing about classical physics? It once thought itself invincible. Seriously. By the end of the 19th century, many scientists believed they had almost solved the entire puzzle of the universe. Only a few small details left to polish. They thought if they just buffed it a bit more, physics would be as perfect as a Swiss watch. Then nature walked in and said, "Oh, you think so? Let me give you a few little riddles." And those riddles, I'm serious, threw classical physics into an unprecedented crisis. It started with black-body radiation. Physicists tried to calculate how hot objects emit light. Sounds simple, but when they applied classical formulas, they got a ridiculous result that became known as the ultraviolet catastrophe. According to classical physics, the hotter the object, the more infinite energy it would emit in the ultraviolet region. Infinite. If that were true, just holding your hand near a hot piece of iron would require the entire energy of the universe to pour into it in an instant. Obviously wrong, but no one could fix it. Then Planck, in what he himself called pure desperation, tried a bizarre idea. Energy cannot change continuously, but only in tiny packets. He didn't know why. He just saw that if he did that, the equation gave the right result. A temporary patch, but accidentally opening the entire quantum era. Then Einstein came in with the second punch. While studying the photoelectric effect, light knocking electrons out of metal, he realized that light cannot be just a wave. If it were a wave, it would deliver energy gradually, but electrons were ejected instantly, as if light were hitting them with sharp blows. Einstein said, "Light comes in individual packets," and so the photon was born. Interestingly, Einstein himself didn't particularly like the quantum idea at the time, but he was honest enough to admit it was the only way to explain the data. Classical science was officially shaken, but it didn't stop there. Bohr stepped onto the stage with a question that gave the whole world a headache. Why don't electrons fall into the nucleus? According to classical physics, an orbiting electron should radiate energy and spiral in within a fraction of a second. So how do atoms exist at all? No answer. Until Bohr proposed something that looked like pure magic. Electrons are only allowed to exist at certain discrete energy levels. Nothing lower, nothing higher. A quantum ladder. No classical physics could explain it, but it matched perfectly with atomic spectra. The bright and dark lines everyone could measure, as if nature said, "This is my rule, not yours." Within a few decades, three small phenomena, black-body radiation, the photoelectric effect, atomic spectra, brought down the entire belief that classical physics could explain light and electrons. Everything that once seemed reasonable suddenly became chaos. The only thing left was the stubborn truth. The microscopic world does not obey the rules of the macroscopic world. And the best physicists of that time had to admit what no one wanted to say out loud. Human intuition is completely useless at the microscopic scale. Quantum mechanics was not born from lofty philosophy. It was born from genuine desperation. No one wanted it to be true, but all the data said it was true. Classical physics could not save itself. It failed to predict black-body radiation, failed to explain electrons ejected from metal, failed to understand why atoms exist without collapsing. And when a theory keeps failing against the simplest experiments, you have to accept that it is only a beautiful model for the large world, not the true language of nature. Quantum mechanics arrived like a stranger, speaking a language that sounded truly uncomfortable. Probability, discrete levels, wave particle, wave function, the role of the observer. Yet strangely, that uncomfortable language described the small world perfectly. It was so correct that it forced us to rethink our entire way of thinking. After all the chaos that quantum mechanics created, you might think that we, physicists, would soon find peace. But no, Nature is never that generous. The next problem was, how do you accurately describe the interaction between light and matter? This is a huge problem, because light is both wave and particle. The electron both has a path and doesn't. And when these two bizarre things collide, the result is a tangle that classical physics simply cannot touch. We needed a new language, a language that describes not just light and matter separately, but the way they dance together at the deepest level. And that is exactly when quantum electrodynamics, QED, was born. If you want a concise definition, QED is the most accurate theory that humanity has ever created to describe how photons and electrons interact. It is not a good theory or a powerful theory. It is the ultimate language when speaking about light and matter. When I say ultimate, I'm not exaggerating. But to show you how strange that journey was, let me tell you about the three people who built it, each walking a completely different path, yet arriving at the same truth. First was Tomonaga in Japan. During wartime, amid chaos and deprivation, he quietly constructed an exquisitely sophisticated mathematical framework, laying the foundation for a consistent quantum version of electromagnetism. Then came Schwinger, who worked with extreme discipline, calculating with the precision of a perfect machine. He could stand against the whole world, armed with only a blackboard and a few pieces of chalk, and usually win. The way he handled mathematics was like watching a solo violinist, beautiful, incomprehensible, and intimidating to imitate. And finally there was me, the one who didn't have the patience for straight paths. I like to draw arrows, squiggly lines, and find a way to describe what was actually happening instead of just accepting equations. I created diagrams, now named after me, and was amazed to see they didn't just work. They worked extremely well. 3 paths, 3 styles, 3 completely different ways of thinking, yet all led to the same theory, QED. If nature did not have a real underlying structure, 3 people taking 3 different roads could never have met at the same point like that. This is not coincidence. This is evidence that we had touched a deeper layer of reality. Now let me tell you what makes QED the most special. Its accuracy. When QED predicts the magnetic moment of the electron, the result matches experiment to the 12th decimal place. You didn't mishear. 12 digits. That's like measuring the distance from New York to Los Angeles and being off by only the thickness of a single hair. No theory humans have ever created, even economics, weather forecasting, meteorology, or even handcrafted Swiss watches, has achieved this level of precision. We are talking about something so perfectly matched that if it were off by just 1 part in a trillion, you would immediately know something was wrong. And to this day, no experiment has ever found an error in QED. Every time we try to test it, it responds with an accuracy that astonishes the world. This leads to an important conclusion. QED is not just a correct theory. It is correct to a degree that is almost unimaginable. But here is the part I want you to pay attention to. This perfectly correct theory, the best, deepest, most accurate description of light, gives us an answer no one expected, that the path of a photon is not just hard to determine. It does not exist as a meaningful concept in nature. If QED is correct, then a photon does not choose one path. It chooses all of them. It explores every possibility. It contributes a piece of itself to every possible trajectory. And it is the interference of all those possibilities that creates the result we measure. You may not like this. I didn't like it the first time I saw it either. It shatters our intuition about motion, about cause and effect, about how the universe should work. But you must remember, QED is not a convenient story we made up. It is verified to every decimal place. And if that perfect theory says predicting the path of a photon is impossible, then that is not our limitation, nor an experimental error. That is the truth of nature. So what really is a photon? I'm being honest. This is the question that makes many students look at me with hopeful eyes. But after I answer, they look at me with disappointment. Not because the answer is wrong, but because they wanted something familiar, something they could picture, draw, or hold. Unfortunately, the photon is not that kind of polite entity. If you try to stuff the photon into the familiar box of intuition, you fail from the very first second. Try the first option everyone likes. Call the photon a particle. Sounds reasonable. Particles move along a path. Particles have position. Particles have trajectories. Particles can go from point A to point B. The only problem, the photon does none of those things the way you imagine. It has no definite position between A and B. It does not travel in a straight line. It does not behave like a marble in a box. The harder you try to force it into being a classical particle, the more it refuses. So try the second option. Call the photon a wave. Waves sound reasonable, right? Waves propagate. Waves interfere. Waves diffract. Light does all of those things. But waves have problems too. Waves don't arrive as individual clicks in a detector. Waves don't come in discrete packets. Waves cannot explain the photoelectric effect the way Einstein described it. Waves cannot account for the quantization of energy. And as you guessed, the photon is not a classical wave either. So what is a photon? The only honest answer is a photon is unlike anything your intuition has been trained to understand. It is a quantum entity, and a quantum entity does not have to obey the models that your evolutionarily shaped brain finds comfortable. It exists in its own language, the language of amplitudes, of probabilities, of summing possibilities, of interference between what could happen rather than what did happen. A photon is neither particle nor wave. It is something that, depending on the situation, behaves like a particle or behaves like a wave. But don't be mistaken. It is not a mixture of the two. It is a completely different entity that we can only describe with quantum mathematics. And this is the crucial point I want you to understand right now. If you ask a photon, "What are you?" it will not answer with words humans have invented. It will only answer with behavior. And that behavior does not follow intuition. When you haven't measured it, the photon can be in a spread-out wave-like state, extended across many possibilities. When you measure it, it appears as a single particle. When you set up the double-slit experiment, it interferes as though it went through both slits. But when you try to find out which slit it went through, the interference disappears as if it never existed. It does not behave as either this or that. It behaves as something that is neither, yet can be either depending on the circumstances. And if this makes you feel unsteady, don't worry. That's a good sign. It means you are beginning to escape classical intuition and develop quantum intuition, which is completely different. Now, to return to the original question, to know which path a photon takes, you must first know what a photon is. But as we have just seen, defining a photon in familiar language was impossible from the start. You cannot ask about its path when you don't even have a classical entity to assign a path to. A path is a concept for macroscopic objects, tennis balls, marbles, spaceships, not for quantum units of energy that do not exist in the classical way. Trying to determine the path of a photon is like trying to measure the smell of an equation. It is not technically the wrong question. It is wrong at the foundation. And if you think things only get confusing when we do complicated experiments, let me give you a simple example you can do right in your bathroom. Look at the surface of water. I'm not talking about the ocean, or waterfalls, or big lakes. I mean an ordinary glass of water. When light hits the surface of water, about 4% of the photons are reflected back into your eye. 4%. That number doesn't change whether you pour water into a glass tumbler or a porcelain bowl, whether the day is sunny or cloudy. At near normal incidence, water reflects 4%. Sounds neat, right? But here's where physics gets interesting. There is no way to know which photons will be the ones that reflect. There is no secret criterion on the water's surface that says this photon is allowed to bounce back. That photon must go through. No mark, no microscopic defect, no surface terrain, no dust particle, no crystal structure, nothing. Every attempt by classical physics to explain this has failed miserably. You cannot look at a photon and say, oh, I think this guy looks like the type that likes to reflect. Photons don't carry license plates. They don't carry ID cards. They don't leave footprints on the water before you detect them. They just do what they do. And the only way to describe their behavior is with probability. And if you predict by flipping a coin 100 times and saying, I think 4% will reflect, then congratulations. You have already done better than every classical theory that ever tried to describe this phenomenon. Your random guess is more accurate than centuries of people working to describe it with classical models. This may make you uncomfortable because humans hate randomness. We want reasons. We want mechanisms. We want a nice answer like the photon reflects because of this or because of that. But nature looks at you and says, no, 4% is 4%. Stop asking for more. You might think, maybe the water surface isn't perfect. Maybe photons interact with electrons in water molecules in a way that creates distinction. But every idea like that collapses when you test it in more perfect environments. Ultra-pure glass surfaces, polished metal in vacuum chambers, or artificially engineered nano surfaces. They all give the same result. You cannot predict which photon will reflect. The problem is not the imperfection of the surface. The problem is the way nature operates at the quantum scale. Each photon carries an amplitude for reflection and an amplitude for transmission. QED describes this with extreme precision, but it never assigns the photon a specific decision before the interaction. You can calculate the probability accurate to 12 decimal places, but you cannot know the outcome for any individual photon. This is very important because it completely destroys the classical idea of path. If you cannot predict which photon will bounce back, how can you assign it a single path? A path is a concept for objects with definite behavior, but the photon has no definite behavior. It is a quantum entity, and its behavior can only be described by probability, not by straight lines or curves. Imagine this. You stand in front of a door, and 4% of the millions of people walking through it suddenly bounce backward, with no criterion whatsoever. No predictability, no pattern, no correlation with speed, height, weight, or mood. What would you conclude? That the door has special paths reserved for certain people, or that the phenomenon does not follow ordinary intuition about motion? That is exactly the situation with the photon. If the fact that 4% of photons reflect with absolutely no private reason of their own has already shaken your intuition, then brace yourself, because what I'm about to say next will force you to rethink your entire concept of motion. We are approaching the very heart of the matter, an idea that sounds completely crazy, yet it is the cornerstone of QED, the thing that allows us to predict photon behavior with the highest accuracy in human history. The idea is that the photon does not travel along any single path. It travels along every possible path. I'm not speaking metaphorically. I'm not joking. I mean it in the strict mathematical sense. Between any 2 points, A and B, the photon considers every conceivable path. Straight lines, curved paths, zigzags, spirals, loops, wiggly routes, paths that go around the moon or swing behind your back and come back. Every single one of those paths contributes to the behavior of the photon. You heard that correctly. Every path, literally every path. If you feel that this is utterly absurd, congratulations. You are reacting exactly the way the first physicists reacted when they encountered the path integral method. Why? Because our entire classical intuition is built on one single idea. Objects follow an optimal path. A stone falls along a definite trajectory. A ray of light travels in a straight line. The earth orbits the sun along one unique orbit. Our brains love clear, tidy, clean paths, but the photon never signed that contract. In the quantum world, nature does not choose the perfect path. Nature considers all paths, then lets those paths compete with one another through amplitudes. Those little rotating arrows I promised to talk about soon. Paths that produce arrows in phase reinforce each other. Paths that are out of phase cancel each other. The final result, the sum of all those possibilities, is exactly the behavior you observe. That is why light appears to travel in straight lines, not because it follows one single path, but because all the loopy roundabout paths cancel each other out, leaving only the straight path with phases aligned enough to add up strongly. But if you change the conditions just a little, like in the double-slit experiment, you create a situation where paths that used to cancel now reinforce each other instead. And suddenly light starts behaving as though it traveled along every possible path, including ones you never even imagined. Let me say it clearly. The path integral is not a mathematical trick. It is not a convenient calculation method. It is not a philosophical hypothesis. It is the most honest description we know of how nature actually operates at the quantum level. If you ask a photon, which path did you take? It will answer, all of them. And if you press further no, I mean, which path did you really take? The photon will reply, you're asking the wrong question. Humans are used to thinking in terms of one single path, because that's how everything big behaves. But the photon does not live in our world. It lives in the world of probabilities and amplitudes, where every possibility has a voice. To help you picture it, imagine an election in which every possible route gets to vote. Each path from A to B sends in a vote that contributes to the final outcome. Some votes reinforce each other. Some cancel each other. The actual result you observe is just the net votes left after all the adding and subtracting. The photon travels every path in exactly that sense. And the most beautiful part is when all those votes are added up, the result matches experiment to 12 decimal places. No classical theory, neither mechanics, nor classical optics, nor classical electromagnetism has ever achieved that. Only the path integral does. Let me emphasize once again, because this is the point our classical brains struggle so hard to accept. The photon does not choose one path. It does not have a real path. It has an infinite set of possible paths. And nature, through amplitudes, allows all of them to exist simultaneously, then decides the final outcome by adding them together. If that sounds like magic to you, remember that this is what every experiment has confirmed for decades. Nature does not care whether you find it reasonable. Nature does what it does. If the idea that the photon travels every path still makes you skeptical, then look at one of the most familiar phenomena on Earth, the shimmering rainbow colors on soap bubbles or oil slicks after rain. Those iridescent colors, first described by Robert Boyle in 1710 and later analyzed in detail by Thomas Young in 1801, are not decorative effects of nature. They are the direct result of the photon not choosing path 1 or path 2, but contributing amplitude to both paths at the same time. Let's get a little numerical to see this isn't vague mysticism. A typical soap film is about 300 to 800 nanometers thick. Visible light wavelengths range from 400, 700 nanometers. In other words, the soap film is only a few wavelengths thick. This is precisely the size range where quantum interference becomes extremely sensitive. When a photon, say a blue photon at 450 nm, hits the film, two main possibilities are allowed according to the Fresnel reflection law 1823. One, the photon reflects immediately off the outer surface. The photon passes through the first surface, then reflects off the inner surface. These two possibilities have path lengths that differ by tens to hundreds of nanometers. That difference alone is enough to create a phase shift between the two amplitudes. If the phase difference is 180 degrees, the two amplitudes completely cancel each other. If they are in phase, they reinforce each other. The end result, some colors disappear, some colors become brilliant, some appear only at certain viewing angles. Those colors are not decorative light. They are a map of quantum interference. But the most important thing is this: you cannot assign that the photon took path 1 or took path 2. If the photon reflected from only one surface or the other, you would never see the colored bands. Newton, at the end of the 17th century, tried to explain Newton's rings with a particle model, but he soon discovered that the particle model could not account for the continuously changing patterns. It wasn't until Thomas Young published the double-slit interference experiment in 1801 that the world understood light must have wave properties. But even the wave picture doesn't tell the whole story, because waves do not arrive in discrete units of energy, the way the photoelectric effect explained by Einstein in 1905 requires. It was only when QED was developed by Tomonaga 1948, Schwinger 1948, and myself that the truth became clear. The photon is neither wave nor particle. It is a quantum entity that sends amplitude to every possibility. Let's go back to the soap film to see it more clearly. Change the film thickness by just 20, 30 nm. That's 1/20th of a wavelength, and the entire color pattern changes completely. This terrifying sensitivity cannot be explained by a single path model. It can only happen if the photon considers both paths. And here is modern proof. If you use a single photon detector, such as an APD sensor with a few tens of picoseconds time resolution, and you fire photons one at a time into a 500 nm thick oil film, you still get the familiar interference pattern. Not a beam of light, not a continuous wave, just one photon at a time, and the interference pattern still appears. What does that mean? It means the photon, all by itself, must supply amplitude to both paths. If the photon really chose one single path, then when you send photons one by one, interference could never form. The pattern would never appear. Impossible. Never. But it does appear, and it appears every time, stably, precisely, exactly as QED predicts. One more fascinating thing. If you try to catch the photon in the act by placing a detector at one of the two surfaces, the interference vanishes instantly. Bohr and Heisenberg predicted this in 1927, and hundreds of experiments since have confirmed it. The harder you try to find out which path the photon took, the more you destroy the phenomenon you were trying to explain. Nature does not let you have both interference and path knowledge at the same time. Those two things cannot coexist. So every time you see light changing color in a thin oil film, you are looking at a mind-blowing truth. The photon does not travel along one single path. It leaves traces of two simultaneous possibilities. Only by adding the two amplitudes, as QED describes, can you understand what your eyes are seeing. And if the photon refuses to choose one path in a thin film, only a few hundred nanometers thick, imagine what happens when we put it into more complicated experiments. The story gets far stranger. After everything you've seen, soap bubbles, oil slicks, color bands that appear and disappear just because the thickness changes by a few tens of nanometers, we finally reached the heart of the matter, the amplitude, or as I prefer to call it for clarity, the little rotating arrow. If you understand this arrow, you will understand QED, the most accurate theory humanity has ever created. And you will understand why the photon never agrees to follow one path. Imagine you have a small arrow. It has a tail, a head, a direction, and most importantly, it can rotate. That's what an amplitude is. Not a 0, not a 1, not a go or no go. It is a rotating arrow. Every quantum possibility for the photon, every possible path, every way to reach the detector, every reflection, every transmission gets its own arrow. The direction of the arrow depends on the time the photon takes to travel that path. The longer the time, the more the arrow rotates. For each possibility, we have one arrow, and to know what the photon does, we must add all those arrows together. This is the point where quantum mechanics completely departs from classical intuition. Classical mechanics says, the object follows the optimal path. But QED says, nature considers all paths, then lets the arrows cancel or reinforce each other. The optimal path is only a consequence of that sum, not something the photon chooses. Let's take the closest example from earlier. The two surfaces of a soap bubble. Photon reflects off the outer surface, one arrow. Photon goes in and reflects off the inner surface, another arrow. The two arrows rotate at different rates because the paths are different lengths. When you add them, if they are in phase, they reinforce bright color. If they are 180 degrees out of phase, they cancel dark color. All the colors you see, from purple at 450 nanometers to red at 650 nanometers, come from the adding and canceling of these arrows. A thickness change of just 20-30 nm, smaller than the diameter of a virus, is enough to rotate the arrows a bit differently, and the color pattern changes immediately. QED predicts this with terrifying accuracy. But to see how powerful the arrow model is, let's expand the example. When a photon goes from point A to point B, nature does not choose the straight line the way your intuition says. It assigns a rotating arrow to every possible path, straight curved zigzag up and down, and looping paths that go around. The moon, mathematically speaking, in the path integral. Every path is considered, and the arrow for each path rotates at a rate corresponding to the time that path requires. When you add the infinite number of arrows together, a miracle happens. Long, wiggly path arrows out of phase cancel each other. Near straight path arrows, nearly in phase, reinforce strongly, and the final result is exactly the straight path you observe. The photon does not go straight because it chooses to. The photon goes straight because every other path mathematically cancels itself out. This is the essence of the path integral. I introduced in 1948, nature has no preferred path. It uses all of them and lets mathematics decide which one remains. Now try another example. Reflection from water with 4% probability. How does QED calculate that 4%? Not by asking, does the photon bounce or not, but by writing down every possible path the photon can take when it interacts with electrons in water molecules, then adding up all the corresponding amplitudes. The square of the length of the total arrow, exactly 0.04, not 0.03 or 0.05. Accurate enough to design camera lenses or calculate solar panel efficiency. And this is what I want to stress. Every time you add amplitudes, you are using the real language of nature. Not a model, not a metaphorical story, not philosophy, just rotating arrows plus addition equals sine photon behavior. When we measure an event, like a photon reaching a detector, we see a click. That's probability. But that probability is the square of the length of the total amplitude created by countless rotating arrows. Imagine you have 10,000 arrows, each representing one path the photon could take. Most of them are out of phase and cancel each other. A small group is in phase and adds up strongly. The path you perceive is just the result of that in-phase group of arrows. That is why we cannot assign the photon a real path. It has no path. It has amplitude. It does not follow one single route. It creates probability by letting every route contribute. And most importantly, this is not an artistic choice by physicists. This is what experiments forced us to write down. If you use a classical model, you are wrong by millions of times. If you use classical waves, you can get interference, but cannot explain single photons. If you have grasped how the rotating arrows represent every possibility of the photon, then you are standing right at the door of one of the most beautiful, strangest, and truest phenomena in nature, interference, where nature seems to cancel itself. I know it sounds weird. How can nature cancel itself? But if you look at light reflecting from a thin film, whether a 400 NMA oil slick or the modern anti-reflective coating on camera lenses only 100 nanometers thick, you will see exactly that strange thing happening. Sometimes light reflects so strongly, you have to squint. Sometimes it reflects so weakly, it almost disappears. And sometimes, exactly zero. Not nearly zero. Exactly zero. No photons bounce back. And that happens not because the photon took the wrong path, or because the surface is too smooth or too rough. It happens because the rotating arrows cancel each other perfectly. Imagine this. There are two main reflection possibilities from a thin film: reflection from the front surface and reflection from the back surface. Each possibility has an amplitude, that is a rotating arrow. When the photon follows the first path, the arrow rotates a certain amount. When it follows the second path, a little longer, the arrow rotates more. If the film thickness makes those two arrows in phase, pointing the same direction, they add up into one long arrow, and you see strong reflection. If the two arrows are 180 degrees out of phase, one pointing right, one pointing left, they cancel, and the result is no reflection. Not weak, none. Absolute zero. This has been confirmed experimentally for centuries. Augustin Jean Fresnel described it mathematically in 1823, long before quantum mechanics, but didn't know why it happened. When QED arrived, the answer became clear, not because light waves hit each other and cancel, but because the amplitudes cancel each other. This is crucial. Interference does not require real waves. It only requires amplitudes, the rotating arrows of the photon, added together. When they reinforce, we see bright light. When they cancel, we see weak light, or none at all. No water waves, no physical oscillation, no medium carrying waves. Just the mathematics of possibilities. And this is not abstract or confined to the lab. If you have ever seen the anti-reflective coating on camera lenses, a technology perfected since 1935 by Alexander Smakula at Carl Zeiss, then you have seen interference used in the most practical way. The coating is exactly 1/4 wavelength thick for the light it wants to suppress. For green light, at 550 nanometers, the coating is usually about 137 nanometers thick. At that thickness, the two reflected amplitudes from the top and bottom of the coating are 180 degrees out of phase, completely cancel each other, allowing 99% of the light to pass into the lens instead of reflecting. In other words, humans deliberately control interference to eliminate reflection. This can only happen if the two amplitude arrows have equal length and exactly opposite directions. The problem is, if you try to say the photon reflected off this surface, or the photon reflected off that surface, you destroy the model. If the photon truly chose only one of the two paths, complete cancellation would be impossible. There could be no case where reflection equals sine 0%, but it happens every day in every modern optical device. And it only happens because the photon supplies amplitude to both paths simultaneously. To appreciate the finesse of interference, remember, for two amplitudes to cancel completely, the path length time difference needs to be only half a cycle, that is, half a wavelength. For blue light at 450 nanometers, that's just 225 nanometers. That means if the oil film changes thickness by a few percent of a virus's diameter, a few tens of nanometers, reflection can go from brilliant to absolute darkness. No classical model can explain this sensitivity. Only the rotating arrow can. And this leads to a profound conclusion. Interference is not light behaving like a wave, as textbooks usually say. Interference is nature adding amplitudes, possibilities, and letting them cancel or reinforce each other. When we say light behaves like a wave, that is only a convenient description. In QED, there is no light wave in the physical sense. Nothing is oscillating, no medium, no back and forth motion, just the mathematics of amplitude. You may not like that, because the human brain prefers more visual pictures. But nature does not operate to serve our intuition. It operates according to its own rules. Remember this, sometimes strong reflex arrows in phase, sometimes weak reflex arrows nearly cancel, but not quite. Sometimes reflection equals sign. Zero arrows perfectly oppose. All the phenomena you once thought were wave behavior are actually just the result of adding amplitudes. This is why every classical model fails when faced with light. Classical waves cannot explain single photons. Classical particles cannot explain interference. Only the rotating arrow explains both interference with single photons and reflection probabilities accurate to many decimal places. What you see in the interference on oil slicks or soap bubbles is just the cute version of a much deeper, much more powerful, much more shocking truth. Because at some point, you have to stop and say, okay, I get that two amplitudes can cancel or reinforce each other. But what does that even mean when there's only one photon? And this is exactly where the double-slit experiment, first performed by Thomas Young in 1801, comes in like an intellectual explosion that shook the entire foundation of classical physics. Young didn't have lasers, single photon detectors, or multi-ton steel isolation tables like modern labs. He had sunlight, a card with two tiny slits, and a wall to observe on. Yet he produced one of the most important experiments in the history of science. When light passes through two slits, it doesn't shine as two simple bright stripes the way you'd expect from two streams of particles. It creates an interference pattern, alternating bright and dark fringes like stripes. That is the signature of interference. In the classical world, this could only mean one thing. Light is a wave. The wave from slit 1 interferes with the wave from slit 2. But times changed. We now know light is also photon, discrete packets of energy. And then people started asking, what happens if we reduce the light intensity so low that only one photon is in the apparatus at a time? What happens when a single photon goes through two slits alone? Does it interfere with itself? It sounds ridiculous. But in the 1960s, when single photon technology became feasible, physicists began firing photons one by one by one, not as a beam, not as a wave, just one single photon in the apparatus at a time. And what happened stunned the world. One photon at a time. Individual bright spots appear on the screen. Each spot is where one photon landed. But when you let thousands of those spots accumulate on top of each other, a pattern emerges, a complete interference pattern. Not approximately, not faintly, but exactly the same interference pattern Young saw in 1801. The unavoidable conclusion: a single photon must go through both slits in the quantum sense. It must send amplitude to both the possibility of through the left slit and through the right slit, just like it did in the thin film phenomenon. But this time you can't blame it on many photons piling up. This is one photon alone, and it still produces interference. Nature is telling you, I don't need many photons to interfere. One photon is enough to force you to throw out all your old intuition. But the story doesn't end there. Physicists didn't give up so easily. They asked, okay, the photon interferes when we don't observe its path. But what happens if we try to watch which slit it goes through? And they placed a tiny detector at one of the two slits, a device sensitive enough to report photon went through this slit or that one. And when they turned the detector on, everything changed instantly. The interference pattern, the beautiful bright and dark fringes, disappeared completely, not faded, not distorted, not slightly noisy, gone completely. Instead, you get two bright stripes corresponding to the two slits, exactly what you'd expect if the photon were a particle, choosing one specific path. And this didn't just happen in the 1960s. It has been repeated hundreds of times, from Jeffrey Taylor's 1909 experiment, using extremely low light intensity, to Alain Aspect's modern single photon experiments in the 1980s, to ultra-sensitive detector versions, to fully quantum versions in the 21st century. Every repetition says the same thing. When you don't look, the photon interferes. When you look, the photon does not interfere. And this leads to the most shocking truth of all. There is no path before you observe. If the photon had a real path, meaning it chose left slit or right slit from the beginning, then whether you observe or not should not change the outcome. But the outcome changes completely. If you place a detector to see which slit the photon went through, the two amplitudes, through left and through right, no longer coexist to interfere. The act of measuring the path destroys the very possibility of interference. Not because the equipment vibrates, not because the photon gets knocked, not because the light is weak, not because the technology isn't good enough, but because nature does not allow you to have both path knowledge and interference. Those two things are fundamentally incompatible. This makes one hard to swallow truth clear. The photon does not have a real path before measurement. No trajectory, no route, no story about which slit it chose. When unobserved, the photon exists as amplitude, spread across both possibilities. When observed, the amplitude collapses into one single possibility. But that collapse moment does not mean the photon was always going that way. It only means that is the outcome you forced it to give. Measurement does not reveal a path. Measurement creates a path. And that, my friend, is why the double-slit experiment stands as absolute proof that the idea of the photon follows one specific path cannot exist in quantum physics. It is not something to find. It is not something to measure. It is not something that exists before you ask the question. The photon does not go through path 1. The photon does not go through path 2. The photon does not split. The photon does not choose. The photon only supplies amplitude. And nature decides the rest. If this makes your entire foundation of perception tremble, congratulations. You are standing before one of the deepest truths of the universe. There are questions that only make sense once you stop trying to impose on nature concepts that do not belong to it. And which path did the photon take is one of those questions. After witnessing the double-slit experiment, where the photon self-interferes when unobserved, but instantly becomes a well-behaved particle, going through one slit when we try to track it, you may begin to feel that the problem is not with the photon. The problem is with the very question we are asking. And this is one of the most important philosophical lessons physics has ever taught us, and taught us brutally. The real path is not something nature uses to describe the world. It is something humans invented. Humans invented paths because we grew up in a macroscopic world where balls fall, cars drive, birds fly, all of them having position and trajectory. We are used to tracking things from point A to point B. Our brains evolved to predict the path of prey, to throw spears accurately, to time when to open a door. For us, path is the most natural idea in the world. But nature has no obligation to share that intuition. When you go down to the quantum world, you are leaving the realm where your brain was designed to work well, and you start seeing things that classical intuition simply cannot grasp. Let's go back to the photon. When you don't measure, it interferes, meaning it exists as a superposition of all possibilities. When you measure, it appears at one single position, as though it always went one way. But that does not mean it always went that way. It only means that is the way your measurement forced it to give. This is an extremely important distinction that many people miss. They think measurement is just reading off the photon's path. But no, in quantum mechanics, measurement creates the outcome, not reveals something pre-existing. The truth is not waiting before the measurement. It is determined by the measurement. So when you ask, which path did the photon take? You are using a concept that does not exist in the system the photon operates in. You are like someone asking, what is the color of a melody? Or what does an equation taste like? Those are wrong category questions, wrong domain questions, questions with no real object in nature. The real path, meaning one unique trajectory, is a beautiful concept in classical mechanics, but it fails completely in quantum mechanics. A path only makes sense when an object always has a definite position at every moment. But the photon has no definite position between source and detector. It has amplitude. It has possibility. It has an infinite set of paths, and nature uses all of them in the calculation. If you force it to choose one path, you are destroying the very mechanism QED describes. Remember the interference pattern. It only appears when the photon does not choose. If the photon had already chosen one slit from the beginning, there would be no way for the interference pattern to form. That truth has been verified for over 100 years, from Taylor in 1909 to Aspect in the 1980s, to modern experiments with superconducting single photon detectors in 2015, 2019, 2023. All of them say the photon has no path before measurement. There is no such thing as the real path, only amplitude. And amplitude only becomes one single outcome when we perform the measurement. In other words, the axiom the photon has a real path is not part of physics. It is part of human thinking habit. And it is precisely because of that habit that we feel quantum mechanics is weird. Nature never promised that everything small must behave like a pebble or a marble. That is what we expected. Nature is not weird. We are just asking weird questions. That is why when someone asks me, why can't we know the real path of the photon? I have to answer, because the photon does not have a real path for you to know. The path is a product of macroscopic intuition. The photon does not live in that intuitive world. It lives in the world of amplitudes, of interference, of measurement determining outcome. When you understand this, you begin to see the bigger truth. The problem is not that the photon is mysterious. The problem is that our intuition does not fit the real structure of nature. And that is exactly why you cannot measure the path of a photon. Not because of technical limits, but because of the limits of the very concept of path. Sometimes a wrong question does not need an answer. It just needs to be abandoned, because nature doesn't think in straight lines. We do. So what really happens when you try to catch the photon in the act of taking a path? This is where we enter one of the most famous problems in quantum mechanics, the measurement problem. And if you think this is just some technical detail physicists argue about in conferences, let me be blunt. No, the measurement problem is what decides whether you see interference or not, whether the photon takes a path or not. even how one possibility becomes reality. Without the measurement problem, the entire quantum world would make no sense. Let me tell it in a more everyday way. Imagine you ask a child, "What flavor of ice cream do you want?" And the moment you ask, the kid is forced to pick one answer, even though before that he was imagining 10 different flavors. If you don't ask, he keeps all those options in his head without having to drop any. But your question forces him to decide, to collapse down to one single answer. Measurement in quantum mechanics works exactly like that. When you don't ask the photon which path it took, it keeps every possibility. Literally every amplitude exists in parallel. But the moment you ask, your question forces the photon to do something it had never done before. Choose one of those possibilities. And the instant it chooses, the entire amplitude structure collapses. Interference disappears. The rotating arrows that were adding up to create interference are instantly replaced by one single arrow. You no longer have a rich set of possibilities. You have one naked answer. This is why physicists often say, every time you ask the photon which path it took, you force it to pick an answer it had never picked before. The photon has no path before you ask. Your question creates the path. You are not observing a pre-existing truth. You are forcing nature to give a specific answer. Let's go back to the double-slit experiment to see this most clearly. When you don't place a detector at the slits, the amplitudes through left slit and through right slit both exist, rotating in mathematical space as two arrows contributing to the final result. They interfere, reinforce, cancel, and create the beautiful bright and dark fringe pattern on the screen. But when you place a detector at the left slit, what happens is not that you track the photon, but that you force it to become a photon that went through the left slit or went through the right slit. You are forcing nature to discard all other possibilities. In the language of QED, before measurements left amplitude plus right amplitude plus right amplitude, interference after measurement, only left amplitude or only right amplitude, no interference. And this is not a flaw of the apparatus. The photon didn't bump into dust. The experiment wasn't imprecise. This is a foundational principle of quantum mechanics. Experiments from the 1920s to today have repeated this with countless different techniques: detectors, polarization, path-separating devices, even Rydberg atoms to tag the photon's journey. Every time we try to observe, all parallel possibilities collapse. And the cruel part is, you cannot observe more gently. There is no such thing as looking without affecting in quantum mechanics. Observation always has impact. Impact always destroys interference information. Nature does not give you the result for free. And the price you pay is exactly the collapse of all the possibilities you wanted to keep in order to understand the phenomenon. Here's a fun example to make it easier to picture. Imagine you're watching a magic show where the magician appears simultaneously at two places on stage thanks to a special technique. The performance is beautiful, but you're curious and run backstage to see where he really is. The moment you open the door, you only see him standing in one single spot, and the instant you go back to the stage, the magic disappears. No more simultaneous positions. Quantum physics works exactly like that, except here the magic isn't a trick. It is the real structure of nature. When you observe, you dismantle the magic yourself. You destroy the phenomenon you wanted to understand. That is the measurement problem, and it leads to the most important conclusion of this section. You cannot know the path of the photon because measuring the path destroys the very thing you wanted to observe. The photon is not hiding its path. It has no path. But when you insist on asking, you create a path, a fake answer that nature is forced to supply when the amplitude collapses. If you think the fact that measurement destroys the phenomenon you're trying to observe is already headache-inducing, then brace yourself, because nature is about to deliver an even bolder twist The future can decide the past of the photon. Or at least that's the feeling you'll have when you look at John Archibald Wheeler's delayed choice experiment, proposed in 1978 and successfully performed many times from the 1980s all the way to 2007, 2015, with precise single photon technology. This experiment is like a detective movie where the ending changes the meaning of the entire story. A photon is fired toward a double-slit setup, or a more modern version, a beam splitter in a Mach-Zehnder interferometer. The photon starts, travels through the system, and only then, only after, do you decide whether you will measure the path or preserve interference. The decision is made after the photon has already passed the critical part of the apparatus. And the strange thing that happens is the result you get depends entirely on the choice you make later. If you choose the setup to measure interference, the photon behaves like a wave. If you choose the setup to measure path, the photon behaves like a particle. But the photon has already gone through the system. It has already chosen a path, if such a thing as a path exists, before you made your choice. So how can the outcome change? This is the point that makes many people feel as though the universe is going back in time to rewrite the script. But in reality, the photon isn't traveling backward in time to change its behavior. Nature is simply holding all possibilities in a superposition state, an intermediate state, with no path, no wave nature, no particle nature, until you ask the question. And the question you ask after the photon has passed, the slits decides whether the process will be described by the interfering amplitude set or by the path amplitude set. This is physics as thriller. You can change the kind of story you tell about an event after the event has already happened. Picture the simplest version of delayed choice. The photon hits a first beam splitter. At that point, its amplitude splits into two branches, like two possible paths. These branches travel different lengths, then meet again at the end of the device. Right before the photon reaches the final combining point, you decide, do you insert the second beam splitter or not? Insert the second beam splitter, the two amplitudes meet and interfere. You see a wave pattern. Remove the second beam splitter, the two paths remain separate. The photon appears as a particle, no interference. The crucial thing is, you make this decision after the photon has already passed the first beam splitter. If the photon had a path, it would have had to choose at the first beam splitter. It would have had to know which way it was going. But the experiment shows, if you decide to create interference afterward, the amplitudes of both paths still exist to interfere. If you decide not to create interference, the amplitudes of both paths disappear instantly. This could not happen if the photon already had a path from the beginning. The path is only born from the measurement you choose after the photon has passed the decisive part of the apparatus. Modern delayed choice experiments, for example, Jacques et al. In 2007, or the 2015 version, using light from distant galaxies bent by gravity, show this on scales that feel almost surreal. Photons from stars, billions of light years away, seem to decide their behavior based on how we measure them today. But that is not because the photon looks into the future. Rather, the quantum process has no pre-chosen path. The path only becomes a fact when you measure, not 1 second earlier. This is what breaks every classical model. If the photon went left path or right path from the start, you could not change your mind about it by altering the apparatus setup after it passed by. But if the photon, or more accurately, the photon's amplitude, goes through all possibilities, as QED describes, then your decision about which measurement to perform selects one of two amplitude sets. If you measure interferes, you select the combined amplitude set. If you measure path, you select the branched amplitude set. The way you measure affects how the total amplitude is formed, and the total amplitude is the only thing that decides the outcome. There is no classical entity analogous to this. It is not like asking a person, "Which road did you take?" and they answer, "I took the left road." No. In quantum mechanics, the answer only forms when you ask, and the question determines the frame in which the answer is given. In other words, in the quantum world, the answer does not exist before the question. When you hear this, you may want to protest, but the photon has to go through one of the two paths. It can't go through both. The problem is, you are used to classical intuition, and the photon does not live in that intuitive space. If delayed choice makes you feel like the future is whispering instructions to the past, just wait until you step into an even stranger territory. The quantum eraser, an experiment, I always consider nature's most mischievous prank. A prank that shows not only does measurement create a path, but the universe can also erase the very information you tried to obtain. And when that information is erased, the interference pattern, the one that had disappeared, returns as if it had never left. If delayed choice leaves you bewildered, the quantum eraser will make you question whether you've ever truly understood reality at all. Let's start with the most basic story in the double-slit experiment. When you tag the photon's path using polarization, a detector, or any method to know whether the photon went through the left slit or the right slit, the interference pattern vanishes completely. We've seen this, and it tells us when path information exists, whether you read it or not, interference cannot occur. But now imagine you do something absurd. You tag the path to destroy the interference, then erase that path information before the photon reaches the detection screen. It sounds like a bizarre game, but that is exactly the quantum eraser experiment proposed by Scully and Drew in 1982, and most famously carried out by Kim et al. In 1999, using entangled photons. The setup is as follows. You fire a photon through two slits. To know which slit it went through, you tag it by having the two slits produce two different polarization states. For example, the left slit gives horizontally polarized photons. The right slit gives vertically polarized ones. As long as that difference exists, even if you haven't measured it yet, interference disappears. Why? Because the two amplitudes are no longer identical. They can no longer interfere constructively. But now, instead of measuring the polarization to determine the path, you do the reverse. You use a polarization transformer, a half-wave plate, or a special beam splitter to make the polarizations from the two slits indistinguishable again. To recap, initially, photons from the left slit have a different polarization from those from the right slit path. Information exists, no interference. But when you erase that polarization difference, making them completely identical, something absurd happens. Interference returns, not partially, completely. A sharp interference pattern appears as if no one had ever touched the system. This could not happen if the photon had chosen a path beforehand. Nature is sending you a clear message. The existence or non-existence of interference does not depend on which path the photon took, but on whether path information exists in the universe. If the information exists, no interference. If the information is erased, interference returns. In other words, the photon does not remember the path. It does not secretly choose a path and then change its mind. It does not care about the path. It cares about the information structure of the system. This is the point many people get wrong. The quantum eraser does not make the photon go back in time to fix its path. The photon has no path. Not in the present, not in the past, not in the future. The only thing that exists is amplitude, a set of possibilities. When path information exists, the two amplitudes become distinguishable and cannot interfere. When the information is erased, the two amplitudes become indistinguishable and interference returns. Let me emphasize this. Erasing the information is what restores the interference, not changing the photon's behavior. The photon does not go back to change its choice. It never chose. And this is where the quantum eraser becomes almost surreal. In the version using entangled photons, you have two photons, one heading toward the interference screen, the other going into a polarization analysis system. The photon on the interference screen will only show interference if the second photon is measured in a way that erases the path information. But the first photon has already hit the screen long before the second photon is measured. This leads many people to think that measuring the second photon changes the path of the first photon. But that is wrong. There is no path to change. There is no path. What you have is a global amplitude structure in which the system's information determines the kind of outcome you see. In quantum mechanics, the past is not a pre-printed film reel. It is something constructed by measurement. Every quantum eraser experiment confirms this, from Herzog et al. In 1995, using a Mackay-Zehnder interferometer, to Ma et al. In 2012, at the Institute for Quantum Optics and Quantum Information in Vienna, to modern delayed choice eraser versions, where the information erasing device is activated after the first photon has already been recorded. The result is always the same. You cannot find a path because the path does not exist as a property of the photon. It only exists in how you measure. Have a detector, you create a path. No detector, you create interference. Erase information, you restore interference. Path information is what kills interference, not the photon's behavior. And that completely shatters the classical notion that the photon travels along a single trajectory. The quantum eraser is not just a quantum experiment. It is the harshest answer to our intuition. Nature does not keep paths on file for you to look up later. It only stores the information necessary for the amplitudes. And if that information is erased, the world behaves as if the path never existed. So the question, which path did the photon take, not only has no answer, it has no object to answer about. It is like asking, how many kilograms does a symphony weigh? The question is grammatically correct, but fundamentally wrong. The quantum eraser is the final proof. The path is not real, only information is. And information can be erased. And when the information is erased, nature smiles and hands back the interference, as if to remind you that you are the one disrupting the phenomenon, not the photon. Everything you have seen, the photon self-interfering, interference, disappearing when path information exists, interference, returning when the information is erased, delayed choice, making the outcome depend on a decision made after the photon has passed the apparatus. All of it slams into one hard-to-swallow truth. Human intuition was not designed to understand the quantum world. Our brains evolved to throw rocks at prey, avoid deep pits, distinguish the color of ripe fruit, and run faster than the tiger behind the bush. Those skills were excellent in the African savanna 200,000 years ago, but completely useless when trying to understand photon behavior. We are used to objects having definite positions, definite velocities, definite paths. You throw a stone, it follows a trajectory. You push a chair, it slides then stops. That is the world our intuition was trained to understand. But quantum mechanics does not care about those habits. It has no obligation to please the brain of a primate that survived by hunting and gathering. This is the root of all misunderstandings. When you ask which path did the photon take, you are asking with the intuition of a creature living in the macroscopic world, where everything sits in one specific place. But the photon does not live in that world. It lives in the world of amplitudes, where path is not a feature of nature, but merely a tool humans invented to understand the motion of large objects. The harsh truth is our intuition has no common ground with how the world operates at the quantum scale. This does not make us stupid. It just makes us human. Humans do not have intuition for phenomena that happen in trillionths of a second, over distances of a few tenths of a nanometer, with quantities that exist as complex amplitudes rather than position and velocity. We do not see amplitudes. We do not feel phase. We do not experience interference with our senses. Our brains are not built to add spinning arrows. They are built to avoid being crushed by rocks. And that is why everything quantum feels absurd. Not because quantum mechanics is absurd, but because we are trying to use macroscopic world tools to explain a completely different world. Think back to the quantum eraser. All the trouble comes from our insistence on cramming the photon into thought boxes like it went path A or path B. It chose beforehand. It knew. It changed the past. It decided. That is how the brain tries to anthropomorphize nature, turning the photon into a tiny thinking creature. But the photon knows nothing. It does not choose. It does not deliberate. It does not hide information. It simply does exactly what the quantum equations describe, exists as a set of possibilities, and becomes one outcome when measurement forces it to. When you understand this, you see there is nothing spooky in quantum mechanics at all, only human intuition getting punctured. Another example. Many people think delayed choice means the photon senses the future and then changes its behavior. In reality, the only thing happening is that amplitudes do not assign a path to the photon until measurement demands one. But because our brains are accustomed to the idea that an object must always go through one specific place, we unconsciously impose that structure on the photon and then panic when reality does not match. It is that imposition that creates the illusion of paradox. In quantum mechanics, there is no path. There is no coherent story stretching through time like in a movie. There is no tiny object traveling from point to point along a single route. There are amplitudes, and amplitudes are not something you have intuition for. When you accept this, you see that quantum mechanics is no longer strange. It is just different. It is how the universe operates. Our intuition is how our brains operate. The two do not have to match, and when they do not match, the fault is not with the universe. The fault is with us wanting the universe to think like we do. This is the lesson of this section. Intuition is not the compass of quantum mechanics. It is the tool of a brain evolved to survive in a slow, large, simple world. If you want to understand the photon, really understand, you must set intuition aside for a moment and let nature tell its own story. And that story begins with this truth. The small world is not like the large world. The problem is not that quantum mechanics is weird. The problem is that we have the wrong expectation. The quantum world becomes much less mysterious the moment you accept that nature operates with amplitudes, spinning arrows representing possibilities, rather than the clear trajectories our brains are familiar with. And what always fascinates me is this. You do not need to go to a national laboratory or own a particle accelerator to see amplitudes in action. They are present in every technology you use every day, from the laser in the supermarket barcode scanner, to the camera in your phone, to the optical fibers carrying the data you are using to watch cat videos online. All of these devices work thanks to one fact. Most people never notice. Nature does not require the photon to have a path. It only needs amplitudes and a rule for adding them. Start with the laser. A laser emits light in which every photon has the same phase, same energy, same direction of amplitude rotation. This does not happen because photons line up like disciplined soldiers. No one is shouting, "Fall in." inside a laser crystal. What actually happens is that the entire stimulated emission process relies on amplitudes. When a photon passes through the gain medium, its amplitude causes an electron to drop to a lower energy level, producing a new photon with amplitude in the same direction, meaning the same phase. The entire laser beam is the result of countless spinning arrows aligned so strongly that they reinforce each other. No fixed path is assigned to photons in a laser, only a set of mathematically aligned amplitudes. Thanks to this, lasers can cut steel, read Blu-ray discs, guide spacecraft, or measure the distance to the moon with centimeter precision. Now look at a camera, a device you use every day, but few people realize it works entirely on quantum probabilities. Each pixel in a digital camera is a tiny well of semiconductor material. When a photon hits it, there is a probability it knocks out an electron, creating an electrical signal. But the word probability here is not mere uncertainty. It is precisely the square of the amplitude length, the spinning arrow the photon carries. If the total amplitude at that point is large, the pixel is bright. If small, the pixel is dark. Your camera does not record the photon's path. It records where amplitudes allow the photon to end up. And thanks to this probabilistic nature, cameras can distinguish brightness with astonishing detail. Imagine if a camera required knowing the real path of every photon before forming an image. It could not take any picture. Photons have no path, but their amplitudes always know how to add up to create the correct image. And if the camera is not impressive enough, look at optical fibers, one of the most important inventions of the 20th century. Light does not travel like particles in optical fibers. It exists as confined amplitudes in structures called modes. Each mode is an interference pattern of amplitudes, not a path. When you bend the fiber, you are not forcing photons to change paths. You are changing boundary conditions, causing amplitudes of some modes to weaken and others to strengthen. Data travels across the internet from one side of the planet to the other, entirely based on amplitude propagation, meaning probability, not trajectories. You video call, read email, stream movies, thanks to amplitudes, not thanks to highways that photons travel like cars. If photons truly needed single unique paths, the internet could not function. Every fiber would collapse the moment it was slightly bent. Every router would have to calculate trillions of separate routes for each photon. But no, nature is far simpler and more elegant. It only requires amplitudes. Do not forget optical devices like lenses, mirrors, prisms, polarizers. A lens does not bend the paths of photons, as popular books or drawings suggest. It changes the phase of amplitudes at every point across its surface. A mirror does not reflect light particles like a tennis ball bouncing off a wall. It changes the amplitude, magnitude, and rotation direction to ensure one single rule. All amplitudes leading to the final image point must be in phase. That is why mirror reflections are sharp. That is why lenses focus. That is why microscopes can magnify enough to see viruses. No paths, only amplitudes arranged so that one particular outcome happens most strongly. Even GPS, the technology that keeps you from getting lost on the way to the supermarket, relies on amplitudes. Atomic clocks on satellites work thanks to quantum absorption and emission processes, where probability and amplitude phase determine oscillation frequency. If the amplitudes are not accurate to 14 decimal places, GPS errors would make you off by kilometers in minutes. In other words, every time you navigate with your phone, you are trusting spinning quantum arrows. And this brings us to the important conclusion of this section. All modern optical technologies, lasers, cameras, fibers, lenses, GPS, light sensors, operate on a single inspiration. Nature computes with amplitudes, not paths. No technology relies on predicting photon trajectories, because trajectories do not exist. And even when you try to draw a photon's path, the drawing is only a convenient human model, not nature's true map. When you accept this, you begin to read the world in the language the universe actually uses. The universe does not say path. The universe says amplitude. And everything you see, everything you use, everything that lights up your life is the result of those tiny spinning arrows. Once you get used to amplitudes as spinning arrows, and you see how they determine every behavior of light, from lasers to optical fibers, from reflection to camera images, you have gone halfway toward understanding why photon paths cannot be predicted. But to see that this is not just philosophy or failed intuition, we must go to the mathematical reason. The path integral, a formalism I proposed, not because it is beautiful, but because nature forced me to describe it that way. There is no other way, no shortcut, no alternative model. The path integral is the only mathematical machine that describes light correctly to 12 decimal places. And what does the path integral say? It says this: a photon does not travel along a single path from point A to point B. It travels along infinitely many paths. Each path contributes an amplitude. The final result is the sum of all those amplitudes. Infinitely many paths. You may think I am speaking metaphorically, but no, it is a real integral, a sum over an infinite space of trajectories. Every possible path, no matter how ridiculous, looping around Mars or zigzagging like a drunk mosquito, contributes a spinning arrow. You cannot forbid any path. You cannot ignore any path. You cannot say, surely this path does not matter. No, nature does not let you be lazy. In the path integral, every path has a voice, but not every voice is strong. Some paths, the nearly straight ones, near the principle of least action, have amplitudes nearly in phase and add up strongly. The stumbling, twisty, looping paths have amplitudes hostile to each other and cancel out. But the important point is every path must still be included in the calculation. And here is where the mathematical conclusion becomes razor sharp. There is no equation in the path integral that describes the real path of the photon. There is no place for such a thing in nature's mathematical language. Go a little deeper to see why. Each path is assigned an amplitude of the form. Amplitude path equals sine xp. Icasian path. Cos C at pickle orbits in gravity. All of them do not exist for the photon. The only thing you can write is the amplitude for it being detected somewhere. An amplitude is not a path. Amplitude is a spinning arrow in complex space. But to see how truly mathematically impossible it is, imagine you want to know the photon's path in the double-slit experiment. According to the path integral, you must sum every amplitude minus amplitude through left slit, amplitude through right slit, amplitude through left slit, up to the sealer, down to detector, amplitude looping behind the apparatus. Yes, mathematically. Then to the detector. All are valid. All must be summed. Each amplitude rotates at a rate depending on the action. And only when you sum that infinite set of paths do you get the probability of the photon appearing at any pixel on the screen. So the question, which path did the photon take, is equivalent to asking, in this infinite sum of terms, which term is the real one? Nature's answer, all of them are real, or none of them are. The path integral does not pick one term. It uses all of them. You might object, but why no preferred path? Why doesn't the photon pick an optimal one? The answer is, because that is how nature works. The path integral is only correct when all amplitudes are used. Omit even one path, and your calculation is wrong, and wrong to a degree no one can accept. To convince you this is not empty theory, remember QED, The theory based on the path integral predicts the electron's anomalous magnetic moment to 12 decimal places. No other theory in human history achieves this precision. And that theory says there is no path. If there were paths, the path integral would be wrong. QED would be wrong. All laser technology, GPS, quantum computers, cameras, satellites would collapse immediately. But they do not collapse. They work. All of them rely on amplitudes, not on trajectories. Nature chose amplitudes, not paths. And this brings us to the final mathematical conclusion of this section. Photon paths cannot be predicted because mathematics has eliminated the concept of path from nature's foundation. Not because of technical limitations, not because instruments are not sensitive enough, not because photons are too fast, but because the photon has no position between emission and detection. The photon has no path independent of measurement. The photon is described by infinitely many amplitudes. The outcome only appears when amplitudes are sum, and that sum contains no object that can be called a path. That is not a mystery. That is the most beautiful mathematical structure of the universe. And when you understand this, you also understand that asking for the photon's path is like asking the length of a fragrance. The question is wrong, so there is no right answer. The entire story of the path integral, infinitely many paths, each with an amplitude, all summed to produce probability, leads us to a paradox so beautiful that it leaves many physicists both astonished and despairing. Nature provides no real path for the photon, yet allows us to predict where the photon will appear with unprecedented accuracy in the history of science. You cannot know which path the photon took, but you can know exactly which paths it did not take. You cannot track a trajectory, but you can measure probabilities to an error of about 1 part in a trillion, equivalent to measuring the distance from Earth to the moon and being off by less than the thickness of a human cell. This is what I call the art of calculating probability. Not telling stories about tiny objects flying along curves, not building models of quantum tennis balls, not drawing tiny trajectories and pretending they are real paths. No, QED discards all of that and cares only about amplitudes. And by summing those spinning arrows, QED predicts everything involving photons and electrons with terrifying accuracy, accurate enough to make you wonder, how can a theory that knows nothing about paths predict more precisely than all theories that did assume paths? Look at the most famous example, the electron's anomalous magnetic moment. Experiment traps an electron in a magnetic field and measures its precession frequency. QED calculates that value by summing amplitudes from millions of imaginary paths, twisty paths, curly paths, paths looping through possible worlds you cannot even imagine. And the result matches experiment to 12 decimal places. That means if you write down the theoretical and experimental values, you have to go to the 13th digit to see a difference smaller than a bubble in an ocean of numbers. No classical theory has ever achieved this. No theory in economics, biology, sociology, or even fluid mechanics reaches this precision. No theory, not even Swiss watchmaking, famous for precision, reaches the 12th decimal place. But QED does, by accepting that the photon has no path. This is not a paradox. This is elegant truth. Nature does not care about paths, but cares extremely seriously about probabilities. When you ask, which path did the photon take? Nature cannot answer, because that question is not in the universe's program. But if you ask, what is the probability the photon arrives here? Nature answers with a number so precise you cannot distinguish simulation from reality. And in quantum mechanics, that is the correct form of question. Not path, but possibility amplitude. That is why I often say QED is not a theory describing tiny objects flying through space. It is a theory describing how nature computes, and nature computes with probabilities. Do not misunderstand. The probability here is not the probability from lack of information, like flipping a coin without knowing your hand strength. No, QED's probability is structural probability, primitive probability, probability that nature uses even when it knows all possible information. It is not a gap in knowledge. It is the essence, and QED's accuracy proves this. Any attempt to assign trajectories to photons, whether hidden paths, latent paths, real but unmeasurable paths, immediately breaks QED's mathematics. If you add a trajectory, you face two mathematical tragedies. One, you destroy interference. Two, you destroy the accuracy. Both are completely wrong compared to experiment. In other words, adding paths to the quantum description adds error. Look at the camera. QED predicts the probability of a photon hitting a pixel so accurately that cameras can photograph stars millions of light years away. Look at the laser. QED predicts the mulated emission probability so accurately that lasers maintain monochromaticity over hundreds of kilometers. Look at optical fibers. QED predicts the light loss to thousandths of a decibel per kilometer. No model based on photon trajectories can approach that accuracy, and we must accept this. Every technology of modern civilization works not because we know the paths of photons, but because we accept that photons have no paths. You live in a universe where probability written in amplitudes is the deepest truth. No straight lines, no curves, no zigzags, no photon running from here to there. No story you tell a child when explaining light. Only amplitudes. And amplitudes, when summed in an extraordinary, almost artistic way, produce the probabilities we can measure, predict, verify. The universe does not tell stories. It does not describe actions. It only provides a probability map. And this is the deep reason you cannot predict the photon's path, can predict all its behavior. QED is not a theory of trajectories. QED is a theory of probabilities calculated via amplitudes. When you understand this, the so-called contradictions disappear. You no longer doubt. You see the universe is not messy. It simply does not use human concepts. We do not know the photon's path because the path does not exist, but we know exactly how all possibilities interfere to produce the final outcome. That is the art of calculating probability that nature has written into the mathematics of the universe. Coming this far, you might feel a bit disappointed. After all the sophisticated mathematical tools, the experiments that set intuition on fire, the bold conclusions that the photon has no path, no reality in the classical sense, you might blurt out a very human question. So do I actually understand the photon? And this is when I have to say what many students hear and then want to close the book in science. Understanding is not as important as predicting correctly. You don't need to make nature make sense inside your head. You just need to stop lying about it. Nature does not operate according to your intuition. It operates according to its equations. If you demand that the universe conform to the way the Homo sapiens brain wants to think about the world, you will fail before you even begin. But if you accept the most honest description, no matter how absurd it seems to intuition, you will predict every outcome nature allows. And that is the essence of science. Not understanding in the philosophical sense, but understanding in the sense of predicting correctly. Look at the ancient Maya. They did not understand Newton's gravity. They did not understand orbital motion. They did not understand the concepts of angular momentum or potential energy, but they predicted the cycles of Venus more accurately than medieval Europeans. They did not have the correct theory, but they had the correct formula. They did not understand how Venus operates, but they predicted its position to the day. And that is science at its primitive level. Correct prediction matters more than correct understanding. QED does that at a level millions of times more insane. It does not give you a comforting story about the photon. It does not give you intuitive pictures, does not give you paths, does not give you anything to cling to in the classical world. It only says, here are the amplitudes. Add them up, square the length. You will get probabilities correct to 1 part in a trillion. And when you do that, you see everything match. You see lasers work exactly like that. You see lenses focus exactly like that. You see cameras capture images exactly like that. You see electrons precess exactly like that. You do not understand, in the storytelling sense, the sense of which path did it take? What did it do between emission and hitting the detector? What did it think? What did it choose? Does it have free will? Questions that sound smart, but are completely irrelevant to nature's mathematics. But you predict correctly, and that is the only truth nature cares about. Don't forget that even in the history of science, understanding often comes long after correct prediction. Kepler predicted planetary orbits with stunning accuracy before Newton understood why the orbits were ellipses. Faraday produced electromagnetic induction before Maxwell proved it mathematically. Sometimes theory comes before intuition. Sometimes intuition trails behind, like a child trying to catch up with an adult who just walked into the room. In quantum mechanics, intuition never catches up, and that is perfectly fine. I once said in a lecture, I think I can confidently say that no one understands quantum mechanics in the sense of understanding it the way you understand why a rock falls to the ground. We do not understand, but we predict correctly, and that is what matters. When you demand a real path, you are demanding that nature conform to your expectations instead of describing it correctly. You are trying to force a non-classical universe into a classical brain, and the result is frustration, not because nature is hard to understand, but because you are asking the wrong question. Let me be blunt. Quantum mechanics was not born to be understood. It was born to be correct. And the extraordinary thing is, it is always correct, not occasionally correct, not approximately correct, not acceptably correct, but correct to the point that every other theory must bow to its precision. If the goal of science were to tell comforting stories, quantum mechanics would have failed. But if the goal is to correctly predict nature's behavior, quantum mechanics is the brightest star we have. When you accept that, something very beautiful happens. You stop trying to find paths for the photon because you know they do not exist. You stop asking, what does the photon do when it is not measured? Because you know that question lies outside nature's scope. You stop demanding that the universe conform to intuition because you understand that intuition is a product of evolution, not of truth. And instead, you begin to speak the language of the universe. Amplitude, phase, probability. That language is strange, but it is correct. That language does not comfort, but it is accurate. That language does not tell stories, but it predicts. And in the end, that is what matters. Because in science and in the universe, correct prediction always beats the feeling of understanding. It is strange to realize that after thousands of years of philosophy, hundreds of years of science, and countless efforts to build easy-to-understand models, the most important lesson nature has taught us is this: the universe has no obligation to look reasonable, at least not reasonable in the way humans want. Our intuition is not the compass of truth. It is only a product of evolution. It formed to serve a very specific job: help our ancestors not starve, not get eaten by predators, and hit prey with thrown rocks. Our brains did not evolve to understand photons. They did not evolve to add amplitudes in complex space. They did not evolve to grasp that an entity can exist in multiple possibilities at once and only select one outcome when measured. They were not built to accept that a future measurement can change the content we want to assign to the past. They were even less designed to understand that erasing information can bring interference back, as if the world just reversed time for a few trillionths of a second. They were built to run faster than the tiger. That is why when you look at quantum mechanics, your intuition screams. It can't be that the photon has no path, or it can't be that measurement changes past outcome, or it can't be that interference disappears and returns just by erasing information. But nature does not care about those screams. It does not bother to comfort you. It does not say, okay, I'll behave more reasonably, so it's easier to understand. It simply does what it always does, and your job is not to force it to be reasonable, but to stop demanding that it be reasonable by human standards. Our biggest problem is that we believe the world must obey structures that make the brain comfortable. Objects must have positions. Paths must be clear. Events must happen in temporal order. Information must flow one way. Cause must precede effect. But those are only cognitive habits, not physical laws. Reality did not bind itself to those structures before humans appeared. Everything we call classical logic is only the logic of a slow-living creature interacting with objects trillions of times larger than a photon. A photon has no reason, no biological, no evolutionary, no intellectual reason to obey expectations that a primate brain invents for itself. The quantum world does not care whether you want it to be reasonable. It only cares how amplitudes add up. And if the total amplitude leads to interference, then the photon interferes. If you place a detector that makes amplitudes distinguishable, interference disappears. If you erase the information that makes amplitudes indistinguishable again, interference returns. Nothing in that requires a path. But you cannot help thinking this is very strange, because your intuition has never had to face a reality where information matters more than position, where probability matters more than trajectory, where the future can decide what you think was the past. Yet that is only your feeling, not nature's truth. Humans have always tried to build beautiful stories to comfort themselves. The photon goes through the left slit or the right slit. The electron orbits the nucleus like planets orbit the sun. Atoms are tiny billiard balls, like in textbook drawings. But the more physics advances, the more it forces us to throw away those stories. They are psychological crutches, not honest descriptions. And QED, the most accurate theory humanity has, says something cold but beautiful. The photon has no obligation to make you understand. The photon only has an obligation to obey the equations. I often tell students, you cannot force the universe to be reasonable the way you want, but you can describe it correctly the way it is. The reasonableness we expect is only a reflex of the brain, not the structure of the universe. This is like asking, why don't fish fly? And expecting a philosophical answer. But fish don't fly because evolution did not require them to. Photons have no paths because physics does not require them to. There is no violation of logic, only that your logic is not wide enough to contain quantum mechanics. When you realize this, you start to find nature more comfortable, not because it suddenly becomes easy to understand, but because you stop trying to turn it into something it is not. The universe never signed a contract that it must look reasonable. It never made an agreement with your intuition. It was not designed to be easy to understand. It just is what it is. Our intelligence grew up in the world of animals, But truth lives in the world of equations, and our task is not to make equations resemble intuition, but to learn to let intuition catch up with equations, no matter how much intuition protests. Photons do not obey classical logic, because classical logic is not theirs. They never needed it. They only need amplitudes. And when you understand that, you begin to grasp one of the most beautiful lessons of modern physics. It is not nature that is strange. It is our expectations that are too small. After this long journey, from 4% reflection to soap bubbles, from spinning amplitude arrows to interference, from double slits to delayed choice and quantum eraser, from the failure of intuition to the absolute triumph of QED, you can see what quantum physics has been trying to tell us for more than a century. We cannot predict the path of a photon, not because we lack tools, but because nature has no such thing as a path for us to predict. Every step in this journey leads to the same truth. When the photon reflects at 4%, you cannot know which one will reflect, because the photon carries no label, path. When you look at soap bubbles, colors appear because amplitudes interfere, not because of distinct closed trajectories. When you add spinning arrows in QED, you add infinite possibilities, not infinite real paths. When you open two slits, the photon self-interferes, as if it went through both slits and neither at the same time. When you place a detector, interference disappears, as if the photon went through only one slit. When you erase path information, interference returns, as if the photon was never caught. When you do delayed choice, your future choice determines whether the photon will be described by interfering amplitudes or path amplitudes, as if the past was not yet written until you measured. And when you look at the mathematics of the path integral, you see there is no variable at all for a real path, only amplitudes for every path. Each path contributes an arrow. No path is labeled. This is the real one. No equation describes the photon's trajectory. No hidden trajectory can explain the experiments without destroying QED's terrifying accuracy. All of it points to this. The path is not part of the quantum world. It is only a product of our classical imagination. Humans invented path to describe the macroscopic world. But nature never signed a contract to use the same concept at the microscopic level. The photon is not refusing to tell you its path. The photon has no path to tell. When you ask the photon, which way did you go? The situation is like asking the wrong quantity in the wrong domain, like asking how many kilograms does a symphony weigh? What is the radius of a fragrance? Or what color is an equation? The question sounds reasonable, but the objects inside do not support the structure of the question. The photon exists as amplitude, and amplitude carries no path information. It only carries information about possibility. When you measure, you force the amplitude to collapse into a single possibility, but that collapse does not reveal a real path. It creates a path. It constructs the outcome at the moment of measurement, not earlier, not later. Nature does not care about the story. What did it do in between? In the mathematics of QED, in between has no meaning. There is no variable for position over time. There is no function, xt. There is no trajectory. Only an infinite set of paths in the path integral, all contributing amplitudes, and the total amplitude produces the final probability you measure. If you want to know what really exists, here is the list. Minus amplitudes exist. Minus interiorists. Minus interiorist. 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 What does not exist? Minus interiorist. Minus the class. Independent of measurement. Classical. story you try to impose on the photon, to feel comfortable, and right at this point, everything becomes strangely beautiful. We cannot predict the photon's path, not because the photon is too small, too fast, too mischievous, or because our measurement technology is too poor, not because the universe hides information, not because of some philosophical barrier, but because nature has no concept of path inside its operating model. The path only appears in our descriptions of the large world, where Newton and intuition rule. But the microscopic universe is not a miniaturized version of the large world. It is a different world, with different rules, different language, different structure, a world where amplitude is everything, a world where truth is written in probabilities, not in trajectories, a world where measurement does not just reveal truth, it defines truth. And therefore, the question, which path did the photon take, is not a question we have failed to answer. It is a question nature never asked. When you ask it, you are forcing a macroscopic model onto a microscopic reality, like forcing a two-dimensional map to fully describe a three-dimensional sphere. Impossible, incorrect, incompatible. The wonderful thing is, when you stop demanding that nature look reasonable, it becomes breathtakingly beautiful, not because you understand it, but because you understand how not to understand it. You understand the limits of intuition, the limits of questions, the limits of classical models, and you begin to see that the universe is not alien. It is simply more honest than the simple stories we want to believe. The strange thing is not that the photon has no path. The strange thing is that we ever thought it must have one. And if this is the truth about the simplest thing in the universe, a single light particle, then what do you think is waiting for us deeper, darker, more complex in the quantum world? Subscribe to follow so you don't miss the next journeys into the strange heart of the quantum universe. See you in the next post, where we will continue opening doors that intuition has never touched.